thank you everyone for joining us. I'm pleased to introduce Joerg Schad from Mesosphere. Joerg is the staff software engineer at Mesosphere in San Francisco. In his previous life, he implemented distributed and in-memory databases and conducted research in the Hadoop and cloud area during his PhD. He will be presenting a talk titled Towards Data Science Engineering Principles. Please join me in welcoming Joerg.
Thank you so much. So maybe just a quick raise of hands. How many of you are doing something with data science, machine learning, anything related? Wow, that is really cool. So I'm currently the tech lead for the data science platform topic. And let me just give you the TLDR what this talk is about so you can decide whether you want to stay or leave. So I feel the field of software engineering, the way how we write software, it has been heavily influenced by software engineering principles. So the application of systematic, disciplined, quantifiable approaches to writing software. And any of us who have taken like any classes in that, we've seen like testing approaches, we've seen CI/CD approaches, and just in general, good practices, best practices of how to write software. And just dealing with a lot of big and small companies trying to understand how they should do machine learning, I just wanted to raise that question, is it maybe time to have something similar for data science engineering? I don't claim that I have all the answers. I bring up some points. I would be really curious whether from your experience, everyone who just raised his hand also has some experience, some ideas what might make sense here. And yeah, let's just see how that goes. As said, I'm Joerg. I'm the technical lead staff software engineer for data science. Why do I care about this topic? So at Mesosphere, we work on something called DCOS, Data Center Operating System. And that actually enables building data science platform on top. It's really targeted towards running multiple distributed systems on top of one shared cluster, on top of one shared infrastructure. And this is why, just given my job, I have to care about it. But also personally, I really like the data science topics and everything else surrounding that. Maybe first question, or just stepping a little back, why is machine learning taking off? So machine learning is actually turning data scientists into superheroes. All of a sudden, as we have enough data, as we have enough computing power, we can build more or less self-driving cars. We can do a lot of research. We can discover new things which were really hard or even impossible before. And this is actually possible given this advance of both computing, the amounts of data we have, and also the methods we have in this data science machine learning field. This super Batman over here, Superman, what he wants to do, so the data scientist, he wants to write this awesome ML code. He wants to write really cool models, build exactly this, self-driving cars, AtomNet, make new discoveries by writing really cool ML code. And hopefully he gets like a clean data set. He only has to train it once because his model, of course, is perfect, and all his parameter choices are also perfect. And then once he has trained this one model, he can deploy it. So this is kind of this dream world for a data scientist. Unfortunately, this kind of stops as soon as we start moving away from running TensorFlow on a single laptop. Who of you has run TensorFlow on his laptop? Who has run it in like a distributed production environment? That's fewer hands. And this is exactly where it becomes hard. I really like TensorFlow because it's so easy. I can bring it up on my laptop, a single binary, and I can just get like an MNIST example up and running in probably like 20 minutes, half an hour, maybe tops 40 minutes. And I have my first really easy trained network and success here. If I want to do that more scalable, not only run those small workloads, I might turn to something like Cubeflow. So Cubeflow is running TensorFlow on top of Kubernetes. And that actually already gives me more parts of this data scientist pipeline. I actually get something, it's called Jupyter. Those are notebooks. You can imagine it being the UI, the GUI for a data scientist. If we later on have time for a demo, I can briefly show that. Then we get a distributed TensorFlow setup on this Kubernetes cluster. We get TensorBoard for monitoring our metrics. We get the TF-debug, which is the debugging tool for TensorFlow, and then we also get like a small model serving component. So that already looks pretty complete. Unfortunately, this only works if I'm in a cloud environment. So if I'm running on AWS, GCE, or any of those big cloud providers, this setup works really nicely because I get all the other parts for free. I get something like Spark for data preparation. Usually all those big cloud vendors have a managed service for that. I get cloud storage for free. All the big cloud vendors have cloud storage. And I also get some streaming where later on I can actually have streaming of requests. And with that, I can actually utilize such stack offered by Cubeflow very, very nicely. If I'm in an on-prem setting, so for example, in Europe, a lot of customers dealing with health or personal data, they're actually not allowed to run on cloud vendors. Or other people don't want to tie into a particular cloud vendor because they want to be flexible of moving from one to the other depending on price in the future. And there it becomes more complex because all those pieces, which I kind of got seamlessly for free because they are just available as managed services in the cloud, I all of a sudden have to take care about. I need something like Spark for data pre-processing, data cleaning. I need some storage such as HDFS or Cassandra, and I need some streaming system, typically like Apache Kafka, to stream my requests to my model being served, to have that scalable. And all of a sudden, I actually have to deal with that. So what I, as a data scientist, the superhero, what I all of a sudden have to do, I have to deal with all this around. I have to deal with serving infrastructure, feature extraction, data verification, and only this small black box here is what I actually would love to do, writing ML code, while I'm getting distracted by all those other pieces. And probably this is kind of the first learning a lot of companies we are dealing with are making. Data science is not a single superhero topic. It actually involves multiple superheroes. And here, Robin, he's actually our DevOps, DataOps, or whatever new fancy term you want to use for that. And he's a person who's actually responsible for the entire infrastructure surrounding that so that Batman can focus on his machine learning code and writing really cool models. So in the end, how does it look? So typically, you're starting to build a pipeline like this. So on the front, we have data and streaming. Then this is where the data scientist really shines. We have some model engineering where the data scientist, he can explore data and he can actually build his model. And then typically this model needs to be trained on like a large distributed cluster as we saw earlier. And the interesting piece here is for many companies who are dealing with sensitive data in the finance industry or in the health industry, the data scientist building the model in here, the model engineering stage, he might actually not get access to all the training data because it's too sensitive. So what we have often seen is that the data scientist here, he gets a small anonymized data set to actually build his model. And when it gets trained on this large cluster, which might actually take up a week of time, this is being thrown on another data set in an entirely different infrastructure, just so to keep those data access and data privacy laws in check. After we are done training, so just keep in mind, typically we're not training one model, we are training that for different hyperparameters, so we might end up with 20 models, for example. We need to do testing, and then we select the models we actually want to store and might want to serve later on. And so we have here a model management where we store the actual model plus the associated metadata. So how was training accuracy? What is our serving time? So how long does it actually take to evaluate that model? So if I have different environments, I might want to run my model on a mobile phone, or I might want to run it on a GPU. I actually might want to choose different models here. And then at the end, we need to serve that model. Model serving means we take this trained model and actually expose it to some live queries which we want to answer. So this is a pretty long pipeline, and as said, like the data scientist, he mostly wants to take care of this model engineering. And so the nice piece is like actually like much of the rest, the training, the testing, the hyperparameter optimization, the further optimization of the model, typically we can automatize that using Jenkins, like continuous integration, continuous delivery sometimes even, and that's already like this first clue that we can actually learn something from those software engineering people who have used continuous integration for a while. What's also important is just monitoring all of that. So I, as a data scientist, I mostly care about my models. So I want to use something like TensorBoard to actually monitor the models. If I'm more the Robin, the DataOps, DevOps, I care more about that this entire infrastructure is still running and there's not a failure, for example, in the distributed training after a week, which gets rid of this entire run. So actually, I want to monitor this entire system we are building here. And typically what we want underneath, as we're talking about a number of different distributed systems here, is some kind of orchestration layer. So this can be, as we saw with Cubeflow, that can be Kubernetes, that can be Mesos, or that can be DCOS, depending on your choices here. And now to the core of this talk. So this is the first report where this term software engineering and software engineering principles was coined from the NATO conference in Germany. So I'm from Germany, I like that. And so now the question is, what can we actually learn from that field and where does it make sense to apply it as well? And for me, and working with a lot of people, the biggest challenge is really to have reproducible builds. What I've seen in a lot of companies, at a lot of entities, is this very ad hoc. I have my data scientist, he builds his model, he trains it, he's kind of happy with the performance, then it gets thrown over to the DevOps team who's actually using that for live data. But if a week later, there's some misclassification and legal is actually asking where this misclassification is coming from, it's really hard to track back which model file has been used, so which training model has been trained there, which data set has been exactly used, which cluster settings have been used. So it's kind of really important that, especially if you have to deal with regulatory requirements, finance, healthcare industry, that you actually have reproducible builds. So that means before you throw on your large distributed training, you actually store all the artifacts and kind of a project description. How many of you have heard about MLflow? Databricks actually has stickers for that over at their table outside. So MLflow, it's a new open source project which aims to actually makes it easier to have reproducible builds. So they have kind of a project file which is describing the model, which is describing dataset plus all the dependencies, making it very easy to reproducibly retrain a model if I have to. It could also be just like these servers were lost and I actually have to retrain that. And once I have stored that project file in a scalable fashion, I'm actually able to do that. Important to keep in mind is that there are often a lot of dependencies. So especially if I'm using all those node libraries from a Jupyter notebook, I often had issues recreating that because I didn't pin a specific version. So just recreating such kind of Jupyter notebook sometimes was really hard because I had to track back which dependency, which version of that dependency did I actually use for that run. And this is where version pinning and CI/CD can be very helpful. And in general, just storing stuff in Git. So just having a versioned a Git hashtag commit, and from that, I can actually rebuild my model. So before I'm kicking off this big training run, I typically want to store this file. And how this can work, and this is also kind of the division between those two people, is I, as a data scientist, I work with my data set, I clean it, I prepare it, I spawn my Jupyter notebook where I can work with that data, I can build my model. Once I'm done, I'm actually exporting that into a Git repository. So here, I'm done as a data scientist. And once I have Git commit to some repository, actually the CI/CD system can automatically pick that up. It can take care of the distributed training, testing, optimizations, and then the ends and just store that model. If I want to take that even further, have continuous delivery, I can also integrate that. We'll see a bit of that later during the talk, but kind of this step is automatic, and so it's also much easier reproducible. The second challenge is just requirements engineering at the front. In my opinion, the first question you should ask, do I actually need machine learning? We had an interesting discussion earlier that actually SQL, if I have a small data set and not too complex queries, is a very powerful tool. Also, I feel a lot of people are using neural networks for problems which are actually not applicable to neural networks, and people only use it because this is like the new hype topic. CTO has read about neural networks, so we have to use them. Keep in mind that regression models are also very powerful models. So kind of the first question should be, is that actually a solution to my problem, or am I using machine learning because machine learning is cool right now? Which can also be a reason to use it, but you should just be aware of what is the reason for you to use it. The second most important question is, what data sets do I actually have available? What is the size and what is the quality? Because that can actually also influence the question of what models I can use. Training a 10-layer neural network with a very small data set probably won't be successful. But training a regression model in turn, because it doesn't have that many parameters, might be more successful in that case. So you shouldn't just only ask, do I need this in this case, but also, can I actually use it based on the data I have available here and the complexity my model will have. Then you should ask yourself, what is the target environment? Where do I actually want to serve that? Should that be served from, for example, Coca-Cola has this app where you can scan certain stuff directly from your smartphone. So this is evaluated on the smartphone. And that typically should result in a different model as compared to something I can serve from a large cluster. What model architectures do I want? So if I choose neural networks, what kind of neural network architecture do I want? What kind of problem do I want to solve? Often, and as well, we'll see that in more detail, I have pre-trained models available. So folks like Google, they actually have those large clusters, and they have spent a lot of time and effort in training models. And often I can take those pre-trained models, I throw the last layers away, and I get, for example, the vision recognition for free, and I only have to retrain it with a fairly small data set and fairly small amount of resources. And also, like, how many resources do I have available for actually training this? Because that also, again, depends what tool do I want to choose. Challenge 2, data quality. So this first example, when we start off training our MNIST data set, so this is typically like this first example many people run when they start out using Tensorflow, we get a pre-cleaned data set. And this is why I believe a lot of people are underestimating the value or the challenge of having this pre-cleaned data set. Typically what I see is that people are spending around 50–60% of their time in ETL and data cleaning before they can actually come to this machine learning job. And especially if we're dealing with deep neural networks, it's really crucial. Your model will only be as good as your data quality is. And then typically you need to do some data preparation as well. So you want to turn date formats into one format, convert everything to metric system because that's nicer, and also just have the same distribution. So if values are fairly differently distributed, this might also lead to bad results. And maybe one important story is that this entire data cleaning, data quality, you shouldn't only do that for your training data set. You also need to apply the same principles, the same pipeline to your live training model. And that is actually a story which kind of gave me this idea for this talk. It was a customer. They were actually spending a lot of time improving this data cleaning and data quality part. So they had come up with a really cool Spark, actually multiple Spark jobs, and really cleaned up their data set, trained a new model. It was really cool. Then they moved this model to production, and the quality was just shitty. And what turned out to be the case, they actually were still using the old data cleaning parts on their live data. So their live data was of a totally different distribution and quality than the training data. And if that doesn't match, of course, you get pretty bad results. So this is already like one of those stepping stones that you should apply the same principles to your training data as you should to your live data you actually want to evaluate later on, your cat pictures or your dog pictures. Next thing, libraries. So if we want to choose, there's a lot of tools, a lot of libraries around. So for example, first of all, I have to choose which framework do I want to use. Do I want to use Tensorflow? Do I want to go a level above using Keras? Do I want to use MXNet and XBoost, or which framework do I want to use? Then I have to decide on my model architecture. Do I want like a CNN? So what kind of deep neural network structure, for example, do I want? And then, as mentioned earlier, often there are pre-trained models available. So for example, NNLL is a model available, and Google has a pre-trained version of that available. And then I can just import that as I would do a library in software engineering. And I can just retrain it with a much smaller data set. And so in this case, I actually already get like the embedding, which makes it easy for language processing of getting like embeddings for words. So just keep that in mind that there's a lot of library stuff already around. So you shouldn't be writing. I hope none of us, unless we are in research, is writing ML algorithms from scratch. But most of us, 99.9% of us, we should actually be reusing either architectures or already pre-trained models. Writing those distributed model functions, that's kind of then the next step where we have a lot of choices. So alone in TensorFlow, I have many different APIs and many different ways of actually specifying my TensorFlow code. And the trend is going to this higher level so-called estimator APIs because they're hiding a lot of the underlying stuff. So in the beginning, we were typically writing code somewhere in those middle layers here. And that often involves that we have to understand the actual like underlying cluster infrastructure. We have to know how many nodes there are. We have to address nodes. And if I'm going to this higher level APIs, estimators, this is all hidden away from me. And I don't have to worry that much. And so, for example, in Google, I think over 70% of the machine learning codes they have is in estimator API. And also way more than 50% are actually using those pre-trained models. Okay, next challenge, testing. So keep in mind, and this is also something I've often seen, that you should keep those data sets you're using for training, testing, and then later on validation. This should be separate data sets. And what's a challenge, I believe, is to write unit tests for my models, because I don't really know what should be the output of that, how I can increase that. So a different way of writing unit tests is actually to compare it to previous models. And there's actually a nice way that I can do that with live data. And this is if it's called the so-called rendezvous model. And this happens if my input queue here is like a Kafka queue, for example. And then I can just have multiple models. The Kafka queue, all the models are going to read from that Kafka queue. And let's just imagine like model 1. This is the only one I really care about. This is my current production model. But I can simply compare how model 2 and 3, how their predictions compare to this one model. And so this is a very good way of testing it. Also, depending on your execution environment, you might consider different factors. Accuracy is only one. It might also just be like serving performance. If I'm getting really, really great accuracy on my model, but it takes it always 30 seconds to evaluate, this might not be useful for all the use cases I have. Next challenge, debugging. And debugging, it's more complex depending on which framework you use, especially if you have something TensorFlow, the old model where I have a statically compiled graph, it can be really difficult to understand what's going on, because I first specify how in traditional TensorFlow they now also have like an eager execution. But in traditional TensorFlow, I specify my entire network I can see here, and then I say run this network. So I can't easily debug individual steps, but I have to debug this entire network as one. Luckily, TensorBoard now also has integration for TF-debug. Not sure whether it's still alpha or beta, but I find it much more useful than this old CLI TF-debug, which used to be around for a while. So just keep in mind, debugging neural networks especially is a hard challenge, and it's different from debugging traditional programs. Also profiling. Profiling is really key, especially if we use expensive devices. If we decide to run our code on GPUs, if we are running in Google Cloud, we decide to use TPUs. Those are typically pretty expensive resources, so we should make sure that we can utilize them in a decent way. And therefore, profiling is quite important. And the typical thing I need to optimize for, the first thing I'll see traditionally when I start profiling is that my GPU will be idle 70% of the time. And for that, the next step is typically I need to optimize memory access pattern. And often there's even secret knowledge involved. So for example, NVIDIA GPUs, they have those magic constants. If my data set is, the number of rows, the number of items is a multiple of 16, it all works much faster. And so this is kind of the secret knowledge which is being passed on from data scientist to data scientist. Also, more is not necessarily better. So simply because I can scale out or scale up doesn't mean that it's necessarily getting faster. And so this is where profiling really comes in to understand how can I get the most value for my machine learning models. Next thing is monitoring. We already said those training runs, they can take hours, they can take days. Some really long ones we're getting better, but previously they took even weeks. And so during this time, I as a data scientist, I actually should monitor what's going on there. It shouldn't be like a black box. I come back after a week and I see, oh, been bad. Let's restart from scratch and look again in next week. But therefore, tools like TensorBoard, which allow me to monitor certain characteristics I export during model training, can be very helpful. And so if after a day I see, oh, this model is not going to be great, I can abort that run, change my parameters, and actually start the next one. Second thing we said is that as this is a complex infrastructure, I also shouldn't forget about monitoring that infrastructure. That's probably more the data DevOps persona taking care of that, but it's still very important. The last challenge here is serving. So serving is I have my trained model, I might have multiple trained models, and now I actually want to serve them. TensorFlow comes with its own serving component, but still that comes with challenges. So if I'm having this live, imagine I built a live web service which can classify pictures whether they have cats or dogs, as typical example in machine learning. And now I have this web service where everyone can send pictures. I don't want that this web service is going down simply because I'm replacing the model which is serving. So we need some concepts we already have in, for example, microservices with zero downtime deployments, with canary deployments where I can simply check what is the performance on this new model. And I might actually even serve multiple models in parallel. We have seen this before as kind of a way for testing. But what I can also do is kind of a back decision. So I can actually employ multiple models, and then I take the output of all of them, and I do like an average decision. So if 2 out of the 3 models say this is a dog, then my decision is this is a dog. In terms of serving, we also talked about that there are actually different environments available. And one thing I find really interesting, and that goes into this optimizations I might run later on as well, is to optimize my model for mobile execution. So a typical model can have 10, 20 megabytes, so it's too large and it's too expensive to run on my mobile phone. So there's something called TF Lite, which is taking my TensorFlow model and actually converting it. So typically I end up with 500 kilobytes. It's not as accurate as I'm dropping information, obviously, but as it's much smaller and much better in performance, this can still be very valuable depending on my execution environment. So also if I'm running it on some kind of edge node somewhere far out, not on a big server, this might also be an option because I only have low power available or some other reasons. And so in general, there are different optimizations. So once I'm done training my network, I often do things, I change the integer representation for the weights. During training, it's kind of good to have a pretty precise precision for the way I represent the weights on all the parameters. But once I'm done, I actually can drop precision on that as it's only being used for serving. And that already helps me to save a lot of space and execution speed. So this was kind of like this quick run through the entire pipeline here. So we've seen from like data preparation over model building, model training, model management, model serving. How much time do I have left actually? Okay, sure. Then I can potentially even show. Huh? No, all good. Thank you. So I would suggest we can start out with questions. If there are not enough questions, I'm happy to show a short demo. In general, we have a white paper if you want to read more about data science platforms. Also, feel free to talk to me. Our table is out here. I'll be there after the talk, so just feel free to drop by. And yeah, I would just open up for questions. If there are not enough questions, I'll just move over to the demo.
Hey, so I've got like a data science team, and we're kind of starting building models. We have all those Python notebooks all over the place, right? How do we get from there to here? What's a good step to kind of move in that direction?
So the first step I typically would recommend, because it has the most impact, is of having like this clean interface that the data science team are producing this artifact, which is the model, which is the description of the data I'm using. I said I kind of like this MLflow model file for that, but just figure out what's the best for you, so that kind of the handover from the data science team, the output is a model file from which I know how I can retrain that model. So that's typically the first step I would recommend everyone, because it's going to, first of all, accelerate. It's going to set you up that you can actually go in and easily add here the CI/CD component, because the CI/CD component can simply start off from those artifacts. And that would probably then be the next step, setting up a CI/CD pipeline, which makes the rest of this automatic, because that's saving time from your data science team. They can focus on data science. And again, you're making a huge step towards having reproducible builds and efficient use of infrastructure.
So you said that one of the best practices is to make sure that your data scientists has something that's reproducible.
Yeah.
So that includes like the training data that they use, right? Would you suggest, like, do you think it's a good idea to commit all that training data, especially if it's like a lot of data to get?
No, I wouldn't commit the data to Git. I would commit a reference to Git. Like, you have your data set stored on HDFS, and then you commit the file description plus where you have it stored. Maybe you commit some kind of SHA of that. So what I've seen people do is they just grab a SHA of the entire file and use that kind of to verify that it's still the same file. What I've seen other people do, if they don't care about the exact data, they store some characteristics of the data, like medium, min, max, and that allows them to actually find a similar data set at least to run it. And just keep in mind what they commit. This is actually two separate pieces. One is the model description, plus potentially the data set, but there can be different experiments based on like one model file. So imagine you have one Python file, which is describing your model, and then you can have different experiments against different data sets with different configurations. So there's the model artifact, and then there's kind of this experiment artifact, which is linking a model file with parameters and a data set. Does that make sense?
Yeah.
Any other questions? All right. Joerg, if you wanted to do a demo.
Yeah, I would just briefly show. I have some minutes left.
Yeah, please do.
So just real brief, this is kind of my cluster. So if I look at services, I have here Kafka, Cassandra, HDFS, Jenkins, and my Jupyter notebook. And then for those people who haven't seen a Jupyter notebook, this is kind of like this UI for me as a data scientist. So here, I can even run like a standard terminal. But typically, I, as a data scientist, what I want to do is the launcher. So I want to have like a UI where I can simply, here I can easily write my Python code. If I launch yet another launcher, here if I'm If I'm more like a Scala person, I also can have a notebook kernel where I can write directly my Scala code. And I have similar things for R if I'm an R person. So this allows me as a data scientist, as this is connected to all the HDFS, this is all the security integration. So once I'm in my notebook, I don't have to worry about how do I load my data set. I can simply access because all the credentials has been taken care of. I can launch a distributed Spark cluster from here. And this is kind of this UI from where I can actually do a lot. And I can play with. And what we've seen is, I mean, there are different projects. So this is Jupyter Lab, actually. There's also Zeppelin, which was used way more in the ages of Spark. But actually here, nowadays, this Tori, for example, it's a notebook kernel for running Spark jobs. So I see a lot of that converging onto Jupyter notebooks. And they make it really easy for me as a data scientist because I have an interface I'm used to. I can launch that anywhere. I can launch that on my notebook. And here I can even launch it on a cluster. And that just gives me a very easy, reproducible way to actually have a UI which can access different data sets. Cool. Any other questions? Otherwise, thank you so much and enjoy Big Data LA. Big Data Con LA, right?